All right, hello everyone. Welcome to this session of the MTV Summer School. Today, Tessa will be presenting over organic glass synthesis as well as and characterization. Tessa is a second-year master's student here at the University of Michigan under Dr. Putzi. She graduated the University of Michigan with a bachelor's of science, nuclear engineering, and her research has focused on organic glass scintillators and their applications. Tessa has been accepted to UCLA for nuclear medicine.
Thanks, Ethan. With that, I'll go ahead and get started on my presentation. So I want to start this with a disclaimer. I am not a chemist. So unlike the excellent talk we had on yesterday from Professor Alan Selinger and the talk that's going to be happening tomorrow, my background in the chemistry with this is very limited. I'll try to present it to the best of my ability, but my expertise comes more so in with the characterization side. And another quick disclaimer, I'm also very sick, so if I start coughing all of a sudden, don't be alarmed. I'll mute myself so you don't have to suffer, but just as a warning. Okay,
Also,
so go ahead.
If you have any questions throughout the talk, please post them in the Q&A section, and Tess will get to it either whenever as it comes along or at the very end of the meeting. Sorry, just to let you know that that's there.
Yeah, so just a brief outline to ground the presentation. I'll start with an overview of organic glass scintillators, or what we call OGS. So yesterday we heard Professor Alan Selinger talk a bit about some new exciting types of plastic scintillators, and he mentioned another type of scintillator that was pretty interesting. That was another type of organic, but he didn't go into much detail. And I think some of you were even asking questions like, wait, what was that other type? Which is perfect because that leads exactly into what I'm presenting, which is that other type of scintillator, organic glass. Then I'll talk about melt casting, the process we do at the University of Michigan, because I could speak more to that. We'll also talk about organic scintillators in general, and give a little bit of a background on the physics behind them and how they work the way they do, some of which might be review from some other lectures, but I just hope to give more of a clear baseline as I start to talk more about the experiments we do to characterize organic scintillators. And then I'll talk about some new work that's been done, such as melt blending and incorporating dopants in OGS synthesis. And then I'll end the talk with OGS applications, and then conclude with some really useful reference material that I think you all will enjoy. So for the introduction and motivation, as we know, right, radiation can be detected and quantified with various types of scintillators. And so I won't repeat too much from yesterday's lecture, but essentially incident radiation excites the matrix material. And then through a variety of processes, what ends up is it de-excites as visible light. And there's a picture here showing some OGS square hollow cylinders that we could cast under a black light, kind of showing this process of it emitting and fluorescing. And so organic scintillators can be used in non-proliferation, as we've seen, but also medical applications and high energy physics applications as well. In organic glass scintillators, or OGS, is a pretty newly developed type of material, and it's exciting because it has high light yield, competitive resolution, and additionally a really cool property that you can remelt it and reconstitute it. So I'll go more into the benefits of organic glass here. Organic scintillators in general have worse gamma ray efficiency than inorganic detectors, right? But we like organics because they have superior timing properties and can be sensitive to multiple particles. They have that possibility. And some of the best performing types of organics, which I think you've started to hear about in some of these lectures, is the trans-still beam detector. This is kind of known as like the gold standard among organic detectors, but this is defined as a single crystal. So you have to physically grow it. And that process alone is really time consuming. It's not straightforward at all, and it can limit scintillator volume. On top of that, they no longer commercially produce this still beam detector. So organic glass scintillators, on the other hand, are an amorphous solid, so they're not a single crystal, and you can melt cast them. They're very scalable. They're reusable, right? If you break them, you can just melt them back down and make another scintillator. Additives can be incorporated in a really straightforward process, as well as like loading isotopes to increase sensitivity to particular particles. And then unique geometries are very feasible for different applications. And so this kind of just gives like a brief relation to what some other detectors we've been talking about. So organic glass scintillators are high performing. They're about the same with quantum yields as crystals, which are greater than liquids, which are greater than most plastics. Of course, we've been hearing about some newly developed plastics that are pretty high performing, but this is generally true for especially historic plastics that have been used in the field. Okay, so a little bit more background on now the organic glass scintillator, OGS. Originally developed by Sandia National Laboratories and released in the sense of what we call organic glass scintillators today. I'll talk a little bit more about what I mean by that in a few slides. But the composition is roughly a 90-10 mixture of the primary fluorophore, P2. And just as a recall from yesterday, the fluorophore, what that means is it's just the compound that fluoresces, right? When we have this ionizing radiation impingement on it. And then we add a molecular stabilizer, PB3. And then there's a 0.2 weight percent, so really small in terms of the overall bulk material, secondary fluorophore that acts as a wavelength shifter. So this is bis MSB specifically that they use. And this causes the material itself to emit in the blue light spectrum, which was that slide I showed a little bit earlier, right? And as Professor Selinger was talking about, we want our scintillators to fluoresce in the blue spectrum because that's where most of our readout systems. So essentially, the readout system is kind of like a camera that will take this visible light and convert it to an electrical signal that we can process and quantify as opposed to just qualitatively trying to figure out. So the readouts are tuned to blue light. So that's where they're most efficient at. So we add these wavelength shifters to match that and also to limit self-absorption of the light within its own material. These scintillators are sensitive to both neutrons and gamma rays. And then you can see down here, I have the molecular formulas listed for those main compounds that make up the organic glass P2 and PB3. And there's some references. If you're interested in the chemistry side, these are the people who developed it. So they go into much more detail than I can. But nevertheless, I'll continue on and try to talk more about chemistry. So just generally, types of glasses and different properties that are really important. So we're talking about organic glasses, right? You might be wondering, what is an inorganic glass then? So some examples are like silicate-based oxides or window glass and metallic glasses. Organic glasses, some of the most popular ones you see are like these thermoplastic glassy polymers, but they're not really ideal for scintillation. And this is because they're covalently bonded and they can entangle in longer chains. And so the glasses that we're more so looking at for organic glasses that scintillate are molecular glasses or monomeric glasses. And they're comprised of individual small molecules. So that's kind of the key, is the small molecules piece. And this is like a material science term. And so what we mean by that is that we don't have a long polymer chain, but instead we have individual molecules that are making these up. So that's really important because that means we're not really getting preferential light scattering along like an axis that could be forming. So in addition, we don't follow the long range order of like that crystals would even have too, right? So these are all held together by the van der Waals forces. Which, it's a pretty weak force, but that's why they can be more individualized. And so this plot over here shows some properties of the glass, specifically the volume versus the temperature in Kelvin. And I'm going to go through this and kind of explain to the best of my ability some of the things here. As we have a glass at a high temperature, right? It's in a liquid state. So that means that we have the thermodynamic and energy for these molecules to be vibrating, moving around. But then if we get to a point kind of like right here, what happens is if we cool very, very slowly, like infinitesimally slow along this point, the density is going to drop. Or it's going to increase, I'm sorry, the other way around. So the volume is going to drop. It's going to be like almost a delta function. And it's going to pack very tightly in an ordered form, creating a crystal. That's not quite what we want, right? With these glasses, we don't want it to be a crystal necessarily. We want it to be a glass and be more transparent, not have all that recrystallization. So if we cool it so it goes beyond that point, but still cool it gradually, we can get to more of these glasses that you see over here. And the key here is we need to get past, right, where it's going to just full on become a crystal. But we also want to cool it slowly enough so that we can get a higher density glass and a more stable glass. I'll explain a little bit more what I mean by that in the coming slides. But essentially think of if you cool it super fast, it's, all these molecules are going to be moving around, and then all of a sudden with the viscosity increase, they're going to be kind of like locked into place and frozen, and that's a lot of stress on the sample, so it's not very stable. So if you cool it more gradually, it can create a more stable glass, but you have to be careful because it also means that they have more time to order themselves and become more like a crystal. So it's kind of a balancing act there. But an important property of glasses is the glass transition temperature. And so this is where we go from like a liquid to more of a rubbery flowing state, right? Okay, so now for some history of organic glass scintillators. I briefly alluded to this when I was talking about when the OGS was originally developed. So it wasn't first developed actually by the Sandia National Laboratories. The first report of organic glass used as a scintillator was in 1958, actually. And it had like 60% efficiency of compared to anthracene, which is a pretty common benchmark used among organics. So that was pretty promising. But the problem was that after 4 hours at room temperature, it would fully recrystallize, like you see here, and become very opaque. So that, in addition to just popularization of PVT and polystyrene becoming very available, led people to kind of go away from this. But it's kind of interesting that Patrick Fang and Joey Carlson, who are two chemists at Sandia, who kind of developed the organic glass scintillator as we know it today, stumbled upon this after they even started looking into organic glass scintillators. So they're kind of curious, like, oh, what happened with them? Like, why was this not pursued more? And it was really just that we didn't have stability of the glassy phase. And that's really important. Like, it needs to be able to last at least longer than 4 hours, right? For you to really get use out of it as a scintillator. So this goes into a little bit more detail on how they actually go about more so stabilizing that glassy phase so it stays over not only like 4 hours, but up to much longer time scales than that, so it can be used feasibly. So molecular size has a big impact, and one of the big things about this is free volume. So the denser your material is, the less likely it's going to try to repack itself into a crystal like structure. And so if you have more free volume, it's more likely to try to recrystallize and pack back together. And so in that curve I showed before with cooling the glass, if you were to cool it pretty rapidly, unfortunately I wasn't able to find at least a very good resolution figure. But if you cool it really fast, you actually create a much less dense glass as well. So you get a lot more free volume, and it's going to try to pack back together into more of a crystal structure. In addition, they found that adding other things in there, other molecular components, will add to the stability of the glass. So that's why they added that PB3 that I mentioned a little bit ago. So P2 is their main focus, but they added in PB3 because to ionizing radiation, it looks the same as P2. So as far as scintillation properties, pretty much identical. But the idea is that they're different just enough that it kind of lowers the effective concentration of either P2 or PB3 in a way that it makes recrystallization less likely. So that was a pretty important aspect of the glass. And then this is an equation just taken from nucleation sort of theory, so recrystallizing. And this kind of describes a little bit more mathematically why the free volume is so important. So free volume is related to your number of nucleation sites, and that directly relates to your probability of recrystallization. But I won't spend too much time on those equations. Okay, I am going much slower than I thought I would be going, so I'm going to try to breeze through some of these slides here. But design considerations are really important, right? We want to have high stability, like I mentioned, and good scintillation properties. One thing that's absolutely critical is transparency. These need to be like water, like, glass. When you think of glass, crystal clear, especially when we're talking about bigger bulk material. So things that we care about with scintillators is exciton transport, optical and mechanical properties, compositional variability, because then we can incorporate additives, and then identical molecules too. That's actually particularly important for pulse shape discrimination capabilities, which I'll talk more about later, but I know you heard a bit about in the last lecture. Okay, so now I'm going to talk about our melt casting process, and this is something I am more involved in because we do it at the University of Michigan in-house. So we take the bulk material and, Sandia develops it, and then we melt it down at 200 degrees Celsius, and we apply a rough vacuum. And you can kind of see that's what's happening here on this video on loop, and it's degassing the sample, which is a very important step, actually. And then once that process is complete, we pour the molten degassed OGS into custom silicone molds that we've made. And then we allow them to cool gradually in an oven for about 14 hours. And then after that's done, we pop the samples out of their molds and apply protective polyvinyl alcohol coatings. And then any kind of reflective wrappings that we see fit. This whole thing is lighting up, right? So imagine if we put reflectors on it that'll kind of redirect light into the readout that we care about, which would become just one face of the scintillator. Okay, this is some of the equipment that we actually use in our lab for the melt casting procedure. Pretty low tech, but you can get an idea. We just get metal mold negatives machined. So whatever we want our glass to look like, we'll just say, okay, get a metal piece, machine it to that specification, pour this kind of silicone kit, and let it cure, and we get our molds. So it's really straightforward, pretty low tech, and not that expensive. This goes into a little bit more of the details on why it's so important to degas and go through all those steps that I mentioned with the melt casting process. So you can see the cylinders shown here are some bad examples of when we didn't quite have our process optimized, so we weren't doing everything exactly as we should. But it's to highlight the importance of following that procedure I outlined earlier. So degassing is obviously going to be important because you see we've got bubbles that are just trapped in the glassy state now that exist, and that's going to affect uniformity. Density, though, remember I mentioned how important density is for the long-term stability of the glass, right? So the less free volume we've got, the more stable it's going to be over time, and it's not going to try to recrystallize and become opaque. So that's another important reason. Also, the oxygen, if it's present in there, can cause yellowing long-term, and you can kind of see it in these pictures. In addition, the cooling gradually, as I mentioned before, is going to be preventing a lot of that high stress environment where everything's moving around and then suddenly it's frozen. It'll prevent cracking, and so we'll get a more stable glass if we cool more gradually. And then the polyvinyl alcohol coatings I mentioned, they prevent nucleation sites, which basically is recrystallization, which will make it look opaque. It won't make it look transparent anymore. And this is because the surface itself has a lot of dangling bonds, right, that are kind of mobile. And so if we put on even like a nanometer thick layer of polyvinyl alcohol, it'll prevent a lot of those nucleation sites from growing and taking over the whole surface. So this is particularly important because we have optical greases that we use all the time in detection that if they don't have the PVA coatings, this will only accelerate the recrystallization process. Okay, I'm gonna skip through this slide a bit. This is just talking about internally. We did some work to verify the reproducibility of our melt cast procedure. So we didn't want to be having a process to make these glass scintillators that was really unreliable, right? Then like giving very different results in terms of scintillation performance across different batches that we would make. The kind of highlight of this is that we found that it was consistent across different melt casts, so that was good. Now I'm going to talk a little bit more about just general physics of interactions in organic scintillators, right? So this might be a bit of review, so I apologize for that. But when I get into more of the characterization experiments we perform specifically, this will be really relevant. So it might be a good refresher either way. So our organic glass scintillators are sensitive to both neutron and gamma rays. I've mentioned that. But what does that mean exactly? So a gamma ray interacts with our scintillator material by Compton scattering an electron that exists in the bulk scintillator. And so we need a Compton scattering equation to kind of figure out the physics behind that. And I'll detail that in a few slides. But neutrons, on the other hand, elastically scatter protons. And so this is not quite so straightforward as Compton scattering, which I know you've heard about in the earlier lectures. And so to get more of an idea of what energy it's actually like what energy the neutron was, what it's depositing on the proton, we need to do a lot more extensive characterization with something called like a time of flight experiment, where we could relate the light that we're seeing from the scintillator light output to energy. And so you might have heard the term like MEVEE instead of MEV. And I know it was in the last talk. You probably heard it in some talks before that too. This is why you sometimes hear that MEVEE, because it's electron equivalent. So if you don't perform these pretty involved time of flight experiments, you could kind of just go off of calibrations done with gamma ray sources, meaning that it would be essentially like the electron equivalent, what we would expect for our light output. So just a quick note on that. Now, other interactions like photoelectric absorption are just not statistically feasible in organic detectors. And this slide details why. Organic scintillators, by definition, are low Z, right? It's mainly hydrogen and carbon that it's made up of, and a lot of hydrogen too. So this low effective Z or atomic number means that our probability of photoelectric absorption is really low. If you think about it, right, what blocks gamma rays? Lead, really dense materials. And so if you have the opposite of that, the gamma rays are just going to go right through, and we're not going to get like this photoelectric absorption. And you can see this equation here. We have this the Z to the nth power, where n varies from 4 to 5. And that's in the equation for the probability of photoelectric absorption. So it's extremely dependent on that Z effective. So in lieu of having photopeaks present, we have to use the Compton edge from those equations to identify energies of incoming gamma rays. So this slide goes into a little bit more visual explanations as opposed to me just saying words on a slide. So hopefully this helps all the visual thinkers out there. But Compton scattering, right? This should be a recall. Incoming photon hits this electron, say the L shell. And then what we get is we get the Compton recoil electron and a scattered photon. but this will only partially deposit the incoming photon's energy to that recoil electron. So it's not a full energy transfer at all. The photoelectric effect, on the other hand, hits like more of an inner orbital electron, and we get an ejected photoelectron while the photon is just fully absorbed. And so this is full deposition of energy from the photon to the electron. Now, both of these interactions happen in inorganic detectors, but only Compton scattering really is, for gamma rays, that is going to be happening for organics. And so what that physically means, you can see on this slide here, I've got the equations here with the Compton scattering. I'm not going to make you do math, but it's there. So this figure here shows a spectrum that we would see from a cesium-137 source measured with an inorganic detector. We can see we have a nice gamma photopeak that we would usually use to say, okay, that's what source we're dealing with. And then we also have the Compton shelf, right? The Compton continuum that happens because both interactions are happening in an inorganic detector. Now, what would we see with the same source, but now with a organic detector? This is what we would see. So it looks very different, but this is actually from measuring the same source. And so you got to get a little bit more creative on how to identify sources in this way, how to reconstruct spectroscopic information. Essentially what you see here, if you look at like on the inorganic detector plot, from around 200 to say 500, that's all we're really kind of seeing almost in this organic detector, really just like the Compton scattering. We're not seeing photopeaks. So we have to use this equation here that would tell us the maximum transferred energy to the recoil electron. And that defines a sharp edge because it can't, Compton scattering can transfer no more than that energy. And that's how we would kind of go about reconstructing to figure out the deposited energy from the gamma ray that was incident in the first place. Okay, so there are pretty important scintillator characteristics. I'm from a non-proliferation group, so these are the stuff that we really care about. There's a lot of characteristics, but in terms of light output, you've heard that term sometimes. Essentially what that means is like how much light is a scintillator giving off for a particular incoming energy. And so generally the more, the better. We just get more of a signal. And so you could compare this across cases by using the same system, the same source, same setup, and then just swapping out scintillators and comparing where what we call like that Compton edge, right, where it falls if we take a histogram of the pulse heights, for example. And so if it falls higher, we know we're getting more light output. Additionally, energy resolution is really important. And this one's a little bit easier to understand, right? Just basically how fine can we actually say like that we're looking at a particular energy? How fine can we kind of narrow that with a particular detector? So usually with inorganics, this is really straightforward. You just take the full 1.5 max of the photopeak and use that to relate energy resolution. But without a photopeak, things become a little more complex. And I'll talk about that in the next slides. But just to give more of an overview, timing resolution is also really important, right? This is like for imaging systems, including medical imaging systems. Like if you've ever gotten a PET scan, timing resolution is critical. And by the way, in PET scans, like they use scintillators. So a lot of these same concepts is exactly what's going on with PET scans. But you could perform something called a coincidence timing resolution experiment to quantify that. And something that's really important, like kind of the governing properties of timing resolution, decay and rise times are very important. So with a particular pulse, how fast is it rising up to its peak? And then how long does it take to go back and stabilize back to baseline? And then also pulse shape discrimination capabilities, or PSD, is important too. Okay, so this gets into some of the experiments that we would actually do to characterize organic scintillators. So first, I'm going to talk a little bit about time of flight. And I alluded to that with how important it is to get a good understanding of the actual energy that's being deposited by protons and relating that to the light you're seeing produced by a scintillator. So this shows a setup from a paper by Dr. Tony Shen. You could see it's a little bit hard to tell, but it's labeled. So there's a kind of a trigger detector right next to a neutron emitting source, in this case, californium-252. And then you can place the detector a known distance away. And the idea is that you have your trigger detector that will initially detect a neutron, and that neutron would then scatter and then go into the other organic detector and then trigger. And so you could take the time difference between those two detectors when they're triggering. And if it's, close enough together, like these are moving really fast, so it's very probable that it's the same particle. And if you know the distance between the detectors and then the time it took to travel to them, you can get more of an idea of what the actual energy was of the neutrons. And in this way, get like quasi-monoenergetic neutrons that you could use to fit a relationship between light output and proton recoil energy, or how much that's from the neutron scattering the proton. So you can see that kind of result is shown here, where he does just that. He takes the light output quoted in electron equivalent, right? And then he plots it versus the recoil proton energy, which he finds from this time of flight experiment. And you can tell it's not linear. So this is a little bit more complicated to reconstruct and develop and fit for these detectors. Okay, so the next thing I want to talk about is energy resolution. Energy resolution is a little bit more complicated to do with these. Usually it's pretty straightforward if you have an inorganic, but if you don't, you have an organic that you're trying to characterize, you have to do something, or one of the things you could do, something called a Compton coincidence technique. So there's a cartoon set up kind of showing you what that would look like. So say you have an organic scintillator, and then you would measure some kind of source in coincidence with an inorganic detector. And the events of interest that you're looking for is you're looking for a gamma ray to go from the source into the organic scintillator, and then Compton scatter. And then based off your setup, you should have a known angle that it would scatter back to hit the other detector. In this case, like it's clearly 180 degrees, maybe give or take, because it could go up higher or down lower and still hit the other detector. But around 180 degrees, right, would scatter back and then hit the other detector. So you could apply a time gate to say, I only want to look at events that are happening really, really close together in the organic scintillator and then the inorganic scintillator, because then I'd be pretty confident that that's the same gamma ray. And you want it to Compton scatter the organic, it's going to do that, right? And then you want it, the remaining energy of that gamma ray, to fully deposit in the inorganic via the photoelectric effect. And from there, you should get a backscatter peak in the inorganic detector. And you could do time correlation and energy gating to kind of pull out the events that you're really interested in. And you'll get something that kind of looks more like a photo peak. I mean, it's not really, but it's more of a actual peak that you could fit with a Gaussian, and you could find the narrowness of that peak or the full width at half max and use that to determine your energy resolution. So what I mean is you would get plots that you see like on these slides. So this is after time gating and energy gating based off of this like coincident experiment. And this is the organic spectrum shown. And so you see this prominent peak now. Now we can say how narrow that is and use that to gauge our energy resolution. Imagine if it's really, really thin, then it's really good resolution, right? But if it's really, really wide, then it's bad resolution. So we used a Compton coincidence technique using a cesium-137 source. And we set them up 180 degrees apart. And so you can see now we found the energy resolution for 4 cases, 2 OGS cases and 2 still bead cases. And these were really small cubes. They were 6 millimeter edge cubes, so very tiny. But There's some different reflective wrappings that we used. I'm not going to go into a whole lot of detail on that, but the main thing I want to focus on is how the OGS compares to still bead for light cases. So if we look at either the specular reflective wrapping case or the diffuse, we actually see the OGS is a little bit better than even the still bead, right? And so it's at very least comparable. So this was really exciting because still bead again is that gold standard that we want to get to. Okay, the next experiment I'll talk about is coincidence timing resolution. So there's a lot of ways to determine the resolution in terms of time of your scintillator, but CTR, or coincidence timing resolution, is a way to get system resolution. So that's an important point. It's not just necessarily of the material itself, but the readouts you use, the electronics, all of that. And what you do is you use like two identical as you can make, detectors that are facing each other, and you put a positron emitting source in the center. And in this case, that's sodium-22. Now, if you think back to physics, right, sodium-22 beta plus decays. And so it's going to be emitting these positrons that are going to annihilate with nearby electrons. And what will happen then with that annihilation is we produce two annihilation photons that are emitted in opposite directions. And they're the same energy too. So they're going to be 511 keV photons. And so if you set this up right, you should see that these annihilation photons should like go and hit both of these detectors at the same time if they're, if it's centered and everything. So you could take the time tags of these different detectors and see what the difference is in terms of you'll take a histogram of the difference in time between like annihilation photons, and theoretically, since this should be at the same time, it should just be like a function just at zero. But that's not necessarily the case, and it's not the case because of timing resolution, right? So this is what I mean by that. This is a histogram of the time difference between these two detectors, and the width of that peak is going to tell you the resolution. And so this is an example taken from Warburton, who studied OGS, like inch diameter cylinders, and they performed really well. I mean, this is a competitive resolution that he's quoting here, 200-ish picoseconds for a sodium-22 source with coincidence timing resolution is quite good. Next, I'll talk about pulse shape discrimination capabilities. I know that we talked about it yesterday, but I have these here, so I won't go through too much of what you've already seen, but some things might be new. So as you know, pulse shape discrimination is a detector's ability to distinguish different types of radiation. So if it's sensitive to more than one type of radiation, that's really cool. Like, great. We want to be like able to identify as many as we can on one platform. But it also demands some kind of way to distinguish between particle types, because otherwise, how are you going to obtain spectroscopic information from a neutron if you can't tell a neutron or a gamma ray apart, for example? So there's a way to do it. There's, like lots of different kind of ways to approach this. But what is charge integration with pulse shape discrimination? So the physics idea behind this is that neutrons, as I said, elastically scatter protons, while gamma rays are Compton scattering electrons. Now, which one is heavier? A proton is much heavier than an electron, right? And so for the same kind of imparted energy, the proton is going to have a higher like ionization density as it travels. So it's going to have like a shorter range, and it's going to create a higher density of what we call triplet states. So you can see kind of a graphic down here describing that. And these triplet states, when there's a high density of them, they're more likely to annihilate with each other. And when that occurs, we get delayed fluorescence. On the other hand, with gamma rays, they're scattering lighter electrons. They can move farther, so they have a less of an ionization density. And this produces less triplet states, making triplet annihilation less likely. So the main mode for gamma rays is prompt fluorescence. Instead, we get singlet excitation and de-excitation. So you can see what that looks like is shown in the plot here on the top left. We have a neutron and a photon pulse that are resulting from like the same energy. And you can see that the neutron pulse is more of a tail. Like it's got more of a tail area than a photon. And that's because the triplets are annihilating too. And they are delaying, or they're that's a little bit slower. They get delayed fluorescence there. And so you can take advantage of the shape differences and produce the plot that you see here on the right. So this is the tail integral versus the total integral. And if you chop up these regions and integrate them for the same total integral, which correlates to the same energy, we would expect the neutrons to have more tail integral, right? Because we get delayed fluorescence. And that's exactly what you see here. That's why these two clouds form, a neutron cloud and a photon cloud. And that's how we can sort of discriminate them. And so I'll breeze through these here, but this was essentially some work I did a bit ago on quantifying PSD with different OGS slabs and looking at them. I talk about the figure of merit on this slide, which is used to quantify how PSD capable something is. But the PSD for OGS is very good. And I'll have a table at the end kind of comparing this to other materials. But here it is. So this is kind of a summary looking at light yield and then PSD figure of merit. There's some plastics listed here, but then also I want to highlight our attention on the still beam crystal, right? So we can see that we actually get a higher relative light yield for OGS compared to still beam. And then we get a little bit less of a PSD capabilities. In this case, the higher the better. So the fact that it's a little bit lower, you know, it's very close though. So it's exciting how close it is to still beam. And then something that's really interesting is the scintillation decay time. So that's extremely small with this OGS, especially compared to still beam. Like we've got 1.7 nanoseconds quoted here. Okay, belt blending and incorporating additives. This is getting less or farther away from like my sphere of what I do with OGS, but it's something really interesting that would I'd be kind of remiss not to talk about. So we can alter mechanical properties of OGS. As it stands, it's a pretty brittle material. I myself have broken quite a few OGS scintillators or OGS samples, but that's okay because we can just melt it back down and start over again. But still, you don't necessarily want a very brittle material for all applications. And so you can incorporate things like polymers to increase strength and the hardness. And you can also incorporate plasticizers to influence things like fracture toughness and plasticity. So they're both ways to kind of make it more mechanically robust. One is just like it's going to make it a little bit more, you know, it's going to increase the plasticity, a little more bendy maybe. The other one is like it's just going to make it more of a solid detector. And so this details some of the melt blending work done by Millenbeck, who's a chemist at Sandia and been very involved with the OGS project. The kind of summary here is that he found polystyrene was really good to add into the organic glass. So with P2 being loaded like 60% by weight into styrene 665, which was this particular polystyrene, he found that we were getting really good, like close to what the OGS is performing alone. So it wasn't degrading properties that badly at all. So very encouraging because this is really going to affect our, you know, mechanical properties. And it's a pretty straightforward process to do. Also, it's essentially like grinding up polymers, you know, taking OGS powder, mixing them, melting them down together, stirring them, and then doing the melt cast process. So very straightforward. But you can see here are different scintillators that they produce with different weight percentages of these different OGS in the actual polystyrene. Okay, so another thing we can do is we can add metals into OGS, right? So I've been saying over and over and over again that we don't get photo peaks with organic scintillators, but that's because the effective Z number is really low. But what if we were to actually add in some metals that have a higher effective Z and thus increase our sensitivity to gamma rays? And that's exactly what was done here by work primarily through a company called RMD, where they incorporated tin, or specifically organotins, in a very straightforward process into the OGS material itself. And they were able to see that they were able to resolve low energy photo peaks much better than if there was no tin present in the glass. And they were still able to make pretty clear samples, as you see here. You could also load isotopes for something that we call triple PSD. So triple PSD can refer to sensitivity to not only fast neutrons, but thermal neutrons. And so as it stands, the cross sections for thermal neutrons and like just the hydrogen and carbon that are in the samples is pretty low. But if we put in an isotope like boron-10 or lithium-6, that'll increase our sensitivity to thermal neutrons. And we'll get this kind of island that you see here in that top band on this PSD plot. That represents thermal neutrons. And so this work specifically, they worked with boron-10. Another kind of cool aside is that they found that the boron incorporated aromatic molecule they used, specifically TDB, acted as a plasticizer a little bit too. So it made it kind of softer and easier to work with. So okay, next is applications. I am very much getting close to time, so I'm gonna try to go through this fast. But one of the applications that is work that I have been working on, is why I was looking at glass in the first place, was radio xenon monitoring. We actually have had previous talks on this, so if you're more interested on radio xenon monitoring, lectures given in the past should be available on YouTube on this. But essentially, it has to do with treaty verification. So making sure people aren't exploding nuclear weapons when they should not be. And xenon's a really important part of that. But they use plastic scintillators for parts of the detector that does that work. And a lot of the plastic scintillators they had been using, if they didn't have proper coatings, they would have memory effects, and they just weren't the best resolution-wise. So we looked at replacing that beta cell with organic glass instead. And I'll kind of skip through this slide and this slide. But actually casting the shape that we need for the beta cell, actually, I will go back one slide. This plastic beta cell you see here next to the corner, that is made entirely of plastic and it's hollow. And that's what they would actually use in the field. You'd fill the gas sample you're trying to measure into that. And so it's a very specific shape. That's why we were excited about organic glass, because it's very customizable. And it still is a little bit not super straightforward, right? Because how do we get that test tube shape? So we've been 3D printing PVA molds or polyvinyl alcohol molds because they dissolve in water. So the idea is that we pour the glass into these PVA 3D printed molds, put it in a water bath, it could just take the samples out from there. Other applications that are really interesting, there's something called the NOVO collaboration, and they are doing a lot of work using OGS for proton range verification in medical physics. So proton radiotherapy, if you've not heard of it, is a really exciting emerging modality for treatment because it really limits toxicity to healthy tissue and can target it very excuse me, target very specifically at a tumor location itself due to protons having this feature called a Bragg peak. So this kind of figure here shows dose versus penetration depth. And compared to conventional X-rays, they kind of end up damaging a lot of tissue that's just in the way, on the way to the tumor. So really exciting modality, but verifying the location exactly of this Bragg peak is something that's kind of difficult, and you can get range uncertainties from it. So what this group has been doing is they've been having a series of OGS bars that act as an imager so they can kind of more so identify where that Bragg peak is exactly. Because we don't want it to, say there's a tumor near your liver and you're off a little bit and you're actually doing the most damage to a normal liver. You do not want that to happen, right? And so if you could be, the more certain you could be about this location of the Bragg peak, the better. And so they do that through an OGS imager with back projection. And they've done some really promising work there with some references listed up here. Okay. The last application I'll talk about, it's kind of a shout out. Ricardo Lopez, who's a student at the University of Michigan, he gave a talk earlier in the summer school about his imager, but he uses OGS bars for his specific imager with a HoloLens that serves as a kind of AR interface so that a user could like visually see where a source might be located. So that's really important for non-proliferation and then source location that maybe an inspector would need to use. Okay, in conclusion, we saw that organic glass scintillators are really promising because they offer competitive resolution and in a lot of ways are comparable to the leading still beam material that is also no longer in production. So we definitely need something to replace that. They make incorporating additives much easier. And then although recrystallization and glass stability is a concern, it can be addressed with things like coatings and adding molecular stabilizers like PB3, for example. And we could use OGS in a myriad of applications, right, that I just talked about. So I just want to end this presentation on this reference material. This is a textbook that hopefully is available online for everyone. It's called Plastic Scintillators, and it talks a lot about, it's been published pretty recently, and so it goes into a lot of detail and depth about plastic scintillators and also organic glass. So chapter 8 is all about organic glass. So if you are interested, I would highly suggest this textbook. It's pretty cool. But with that, I will stop. And thank you all for your attention and take any questions.
All right, thank you, Tessa. For any questions you have, please enter into the Q&A part of Zoom.
I see some questions. Okay, the question is if you could clarify on whether the shape of organic glass scintillators has an effect on the application. So do we explore optimized geometries? That's a great question. Yes, it does. So let me go back. Specifically with my work with radio xenon detection, finding the like this shape is pretty important, but other shapes could have like more, say, better scintillation properties because this is a really thin, actually, detector. And so you kind of have to balance like what you need to use actually for its purpose in the field. its scintillation properties. Another thing to note about this is that the walls of this scintillator need to be pretty thin. And there's kind of some decay schemes of the relevant xenon isotopes here. Because this whole beta cell that we're calling it sits in an inorganic gamma cell. And so the walls of those need to be pretty thin with the conversion electrons, allowing them to escape. They're pretty low energy. So that, yeah, optimizing that geometry and tuning it to specific applications is extremely important. And is one of the reasons that I looked into lots of different slab thicknesses and looking at things like pulse shape discrimination capabilities and seeing the effect on geometry there, or at least size. Okay. Since cesium-137 is a gamma emitter, can it be placed in the center between two detectors? Can the detectors pick up the gammas emitted? Yes. So that's kind of the concept behind. Let me go. Oh no, my computer is freezing. But that is kind of the concept behind some of the energy resolution work I talked about. So yeah, so it's a gamma emitter and it's emitting, you know, all sorts of directions. So you can put really as many detectors as you want that'll pick up particles emitted by a source. It really, you know, as long as the source is collimated and it's emitting in all these directions, it really doesn't matter where. You can have like a whole array of scintillators like around this source. And that way you could kind of with having at least two detectors nearby with a source in the middle, you could even detect like the same particle, but as it's scattering from one detector to the other, right? So that's pretty advantageous for us. The next question is my opinion on whether plastic scintillators can be replaced by organic glass. Is there any monetary gains in doing it? That's a great question. There has been a lot of recent advances in plastics that make them really exciting, particularly in their pulse shape discrimination capabilities that just weren't there like a few years ago. So at least not like, you know, maybe liquids had that, but I will say organic glass, I mean, it depends on the plastic that you're buying for sure, but organic glass is hard to say exactly the cost of right now because it's kind of just newly being introduced on a commercial basis. And so I think right now it could be more around like $80 a gram if you want to buy organic glass. So plastics might be around that range, might be cheaper, might be more expensive depending on the type of plastic. But yeah, cost is something very important that I don't think we consider enough, but is extremely relevant for like a lot of actual applications, right? If they can't afford to put a scintillator there and what they need, then it's not going to be much good for them. See one question where plastic scintillators are not recyclable, reusable, but are lasting. Are organic glass scintillators reusable, recyclable? What is their durability? Yeah, that is a great question. So, yes, you can reuse them, which is one of my favorite things about them. You can melt them back down. So say you even break one. As I just mentioned, $80 a gram. Like, imagine breaking a cylinder of that, right? Like, you'd be like, oh my God. But this is an amorphous solid where we could just do a melt casting procedure and you could really just melt it back down even if it's broken and recast it as a scintillator. So from that standpoint, that's another thing to consider going off of the last question from like a cost effective thought. You know, maybe the initial cost is a lot to buy them, or you know, at least maybe not like it's not as much as some other detectors certainly, but maybe it's out of the price range of what some people might have. But you can reconstitute it, remelt it, reuse it. So that's something that's not directly reflected into the initial price you're paying up front, but it's something that's could make it more cost effective in the long run. Oh, and about the durability, whoops, I missed that part of the question. Uh, the durability is uh, the main thing we have to worry about is that recrystallization that'll happen. So it's going to want to get to a more thermodynamically stable state, crystal. And it's going to want to try to pack into that crystal state as much as it can. But then what happens is it's not going to be clear. It's going to scatter light preferentially. It's not going to be ideal for our scintillator purposes. And so, like, as far as stability in that sense, adding things like the other molecular stabilizers like PB3, and then being careful about how you do melt casting, things like that, even molecular sizes that you're determining to use, that all goes into play with the stability of the glass. And then as far as durability, if you're talking about like a mechanical sense, you could do melt blending with polystyrene to have like it will, suffer in some ways the scintillation properties, but it'll be a lot more robust from a like it won't shatter as much standpoint. Okay, and then the last question I see here, main advantage of organic glass scintillators over others. Good question. So among organics, I'll speak from that. Well, I'll back up, I guess. First, I'll talk about why you would want to use organics in the first place. Because organics are a much broader classification that cover plastic scintillators, liquids, crystals, like single crystals like still bead, and these organic glasses, right? So they don't, as I said, have very good gamma ray efficiency at all. And they have pretty poor energy resolution compared to like inorganic scintillators. But what they do have is really fast timing properties. And so that can be really important for you. Like inorganic detectors are slow. And so if you're doing any kind of imaging or something like that, you're going to need as precise timing as you could possibly get. Actually, for PET scanners, getting slightly off topic here, but there's something called the 10 picosecond challenge, where they're trying to get down to a coincidence timing resolution of 10 picoseconds, because that'll like transform how they do PET scans for you, and make it a lot better. And so fast timing, important. But if you're trying to go more so for energy resolution, you might want to look at a different detector, right? Organic scintillators are also, they can be PSD capable, so they could detect neutrons and gamma rays at the same time, or even other particles too. And so if you want that all in the same platform as well, organics are good. Now, organic glass scintillators themselves stand apart among their own group because they're an amorphous solid, so you don't have to physically grow them like a single crystal. Their ability to remelt and reconstitute, and their high performance. Their performance is very high, so that's been a very encouraging thing as well. This last question I think I'll take before, I think this is the last one. I don't want to go too much over time for you guys, are about the applications of gammas from cesium-137 after they're detected. That really depends. You could, if you're talking specifically about this slide, what is happening is it's not necessarily like an application we're looking at as much as it is we're just trying to characterize the material. So characterization is pretty important because we're just trying to evaluate like how good is this. And so here what we're looking at with those gammas is trying to see how finely we can tell like energy resolution. So the more fine we could say like this energy exactly, then the better for, say, if you try to do it for things like spectroscopic information that could be used in reactor monitoring or things like that. So I think those were the questions, but my email is listed here. So if anyone has any other questions at all, please reach out. I love answering questions about my work. So if it's about the chemistry side, admittedly, I might have to point you to someone else. But yeah, thank you all so much for listening and for your questions.
All right. Thank you, everyone.